And we're going to be then moving to a little bit more advanced applications, a little bit more advanced concepts that are going to lead to another exercise type of problem that we're going to be working on more as a workshop type of experience where it will be very hands-on. At least that's my goal. Is to have a hands-on session so that you all can, practice with the software, play with the software. Hopefully, you will be able to install it on your computers. The nice thing about this particular piece of software that is called QGIS is that it is available for all types of applications, including Mac environments, PC environments, Linux, etc. So it's very open in that sense, and it's relatively easy to use. I also wanted to mention that my experience with QGIS is not very broad. I don't use QGIS in my own research, but from what I've learned, what I've seen is a relatively easy application to use and learn. And again, there is no license requirement, which is the problem with some of these other probably more cutting edge GIS software out there. So it's more accessible and also helps, right, in access the technology and also communicate with audiences, which I think is part of what GIS work is about, is creating those type of bridges with communities, with stakeholders, and QGIS I think has a lot of potential. There probably more than this other proprietary type of software that require licenses, a specific license, which could be very expensive. So so we're going to start with, again, this brief introduction to some GIS concepts and modeling concepts, and then work on that exercise towards the end of the workshop. So I think I can share my screen. So I'm going to share, so I can share my screen. So I'm going to share some slides that I put together. So can you all see my screen? Okay. So first of all, a very short introduction about me. I'm a professor in the School of Interdisciplinary Arts and Sciences at the University of Washington, Bothell. I've been teaching and working with GIS for a couple of decades already. So I have some experience also in conservation, doing conservation work using geospatial technologies, remote sensing, GIS, global navigation satellite systems. And a lot of the work that I've done is in the tropics. I'm originally from Ecuador, and a lot of my work is still there. Some field sites that I have are still in South America. So as I said, this is the brief outline of our workshop. First, we're going to start with some views and concepts, GIS concepts in GIS. We're going to also talk about modeling, spatial modeling. Why do we build spatial models? Why are they useful? And what are the goals in some of these types of modeling approaches that we're going to be looking at? Particularly, we're going to focus on one approach that is called multi-criteria evaluation and suitability analysis, which is where GIS has played a very important role for the past 3 decades. So it's a very common approach. There are hundreds of papers that have been published using this particular approach, and I think it's very useful because it's relatively simple to implement, but it's also powerful in the sense that it's inclusive, it's participatory, and we're going to talk a little about where that participation comes into play. So the second part of the workshop, again, we're going to be working on an applied problem related to the identification of a conservation area. Again, there's a hypothetical example, but hopefully that will give us some experience with the data sets, with the approach, and also a little bit of experience with the software. And if you have any questions at any point, please feel free to interrupt me or put your question on the chat. Maybe Bernie or Anna can help me kind of keep track of what's going on in the chat, since I'm probably going to be a little bit, focusing more on the presentation. But I think it's important to have that kind of participation from you guys. And again, if you have any questions, please feel free to interrupt me. Right. So in general, again, we're going to start with some basic GIS concepts. We depart from some conceptualizations, views of the real world. And in GIS, we have two particular type of views that are very helpful. And we use these views or conceptualizations because dealing with the real entities, with the real world entities is impossible, right? So we need to simplify them. We have to model them in a certain way so that we can use computers to look at these features, to understand better how these features interact with each other. And although we think of computers as being very sophisticated technologies, the models that we use, that we generally rely on GIS to build GIS models, to do GIS analysis, are relatively simple. And I wanted to focus specifically on these two that are kind of the basis of what GIS analysis is about. So again, we start with a conceptualization of a real world problem, a real world entity. And there are two different types of conceptualizations in GIS that are also associated with particular data models that we're going to be using. So one of these conceptualizations is what we call the discrete view, which views the world as a discrete space where you have discrete objects populating the space. And we are basically concentrating on types of features. For example, let's think about, for example, streams, right? So we model streams, for example, using lines, using this type of geometry, the line geometry, and everything that is not a stream, we don't represent it with anything, right? So we are representing these different types of information in layers, right? So we separate geographic information in layers. And each layer is of a particular geometry, for example, lines, right, to represent streams. So everything that is not a stream is empty space, right? So we have a stream, we have an empty space, another stream. So we have this type of discrete representation of the space of streams, right? Streams and no streams. So that's one view, right? One view in GIS that's called a discrete view. And we usually represent or use this type of data model, which is called the vector data model, to collect data, to represent information using the discrete view. And in the vector data model, we use points, lines, and polygons to represent the different types of spatial features. The other view that is important in GIS is what we call the continuous view field. Continuous view means that we represent the space, the geographic space, as a continuous set of information, pieces of information. This continuous view is associated with this other type of model that is called the raster data model, in which we represent features or geographic entities using cells, right? So each individual piece of the landscape is represented by a cell. And that cell could represent different things. It could be a stream, it could be a house, it could be some sort of topography, it could be precipitation. But we represent, again, the features not using points, lines, and polygons, but we use pixels, right? Cells to represent the geographic entities. So every single piece of the landscape has information, right? Has a pixel. And that pixel can have, for example, no data. It could be a no data pixel, but still the pixel is there. We can change the information. We can change the value associated with that pixel, and we create information about that particular landscape. Okay, just to summarize. So the vector data model, again, defines discrete objects. So in this example, in this image on the left, we use points, we use lines, we use polygons to represent features. And again, if you don't have points, lines, or areas, there is a vacuum, right? There's an empty space. So that's why we call this a discrete representation, right, with discrete objects. So these are objects that are usually embedded in each other. For example, lines contain points, polygons contain points and lines. So we have this kind of hierarchical system where the point geometry is the simplest geometry. The polygon geometry is the most complex polygon, the most complex geometry. And we have this type of hierarchical system, right? Now, that's how the spatial information is arranged, right? Using either pixels in the raster-based model or points, lines, and polygons in the vector representation. But in addition to the spatial component, that's why I think GIS is a very powerful type of framework to deal with complex data. Is in addition to the spatial component, we also have a non-spatial component that is usually stored in the form of tables, right? Tables associated with those particular type of objects. So we have tables associated with points, tables with lines, tables with polygons, and also tables with arrangements of pixels. So this non-spatial information, for example, let's say, the type of vegetation, for example, land tenure, right? Ownership, colors, right? That's non-spatial information that can also be stored and can be managed, manipulated in a GIS, but using tables, right? So for example, in the vector model, we use tables to organize feature attributes. And we have this type of association between tables, right? These attribute tables and the spatial elements using connections, right? This type of links between the attributes, the spatial objects and the non-spatial attributes. So there is this particular type of connection or relationship between tables and vector layers and vector geometries that is called the one-to-one relationship. That means that one object in your map is associated with one row in the attribute table, right? So that's what we call a one-to-one relationship. And there are different types of relationships that we can build in GIS. So one-to-one is probably the most common one, right? So one polygon, for example, associated with one row in the attribute table. And that's how we connect these two types of information, the spatial and the non-spatial information. So this is just an example, a graphic showing those type of relationships. So for example, let's say that we have this map with 4 different types of units. Let's assume these are, for example, soil units. So we have soil unit 1, soil 2, soil type 3, and soil unit 4. So each one of those units are associated with one row in the attribute table that contains additional information about that particular type of object, that particular soil type, for example. Right? For example, polygon 1 is linked to row number 1 in the attribute table of type A, for example, soil type A, and has an area of 16.8 acres, right? So that's that connection, the one-to-one connection that we have between the vector layer and the attribute table. And information in the vector world, right, with vector data is usually stored in this way, right? Maintaining this one-to-one relationship. So these are just some examples of data that could be represented using the vector geometry, using this discrete view. For example, these are locations of hospitals, for example, in the Seattle area where I live. There's just locations of medical facilities. And as you can see, where you don't have a medical facility, we don't have anything, right? There's an empty space there. So that's kind of this discrete type of representation that we were talking about. So we have another, for example, this is a layer that we're going to be working with today. This is a road layer with roads, and where there's no road, you have an empty space, right? So points, lines, again, a stream layer, and areas, a polygon layer, right? So this is what we call the vector representation. In the vector representation, we have these connections, the one-to-one relationship between spatial objects and non-spatial information. Now, for this purpose, for the purpose of this workshop, we are going to concentrate on this other type of conceptualization, which is the continuous view conceptualization GIS that uses the raster representation, because it's a little bit simpler to implement something that is very important in GIS, which is called map overlays, right? So map overlays using raster data are much simpler to implement than with vector data, with this other type of geometry. So we're going to spend a little bit more time talking about the raster conceptualization. And I think it's also a very powerful type of conceptualization to use in modeling, right? Spatial modeling. So we're going to talk a little bit about those advantages of using raster data for cartographic modeling in a little bit. So again, as I said before, in the raster model, we use cells or pixels to store information. So each pixel has one and just one value. And that value could be whatever you want it to be. For example, it could be precipitation, it could be temperature, it could be, for example, distance to roads, it could be distance to towns, right? So it has to have a value. That value could be of whatever type you want, right? It could be a category, it could be a continuous value, it could be a rank. But the idea is that pixel has a numeric value, and that value can represent anything, right? And we use pixels to provide what we call a wall-to-wall coverage of the whole landscape, of the whole area of the study, right? So there is no gaps. There is no data gaps. Even if there is no information for a particular variable, the pixel is still there, and it could be a pixel with no data, but we can change that value and we can assign a value to that pixel, but the pixel, right, the spatial discrete object is there, right? So that's something that you guys need to keep in mind, that we have complete coverage of everything with no gaps, right? And we're using pixels to do that kind of representation of objects. So there are some examples of continuous data. For example, elevation. Elevation is a very common variable that is usually represented in raster format. Precipitation, for example, concentrations of pollutants, for example. Those are just different continuous variables that are commonly represented using raster data. And raster data is also relatively simpler to manage, and we're going to talk about why that's the case. Because its representation is very simple, right? It's way simpler than having, for example, a polygon representation. A polygon, for example, can be very complex. So the geometry of a polygon could be really complex. But in the raster representation, we're also always dealing with the same shape, right? With the same square shape. And that makes a big difference in terms of managing information, manipulating information, and also performing operations with data. So the raster, in raster representation, there are a few things that we need to keep in mind. First is the dimension of the cell, right? How big the cell is. The smaller the cell size, the higher the spatial resolution of the raster data will be. That means that we can capture more spatial detail if the cell is smaller, right? So if the cell is larger, right, we probably going to have a smaller file in terms of size, but we're also going to have a more coarse representation of whatever spatial object you're representing, right? So the resolution is an important piece to talk about, to describe, because depending on the cell size, the representations of objects are going to change, right? That's probably also one of the disadvantages of the raster model, is that in terms of cartographic detail, we cannot achieve the level that we could if we were working with vector data, right? With lines, polygons, we can have very, very, very important cartographic detail. But with raster, we're limited to the resolution of the pixel, right? So again, if we have larger pixels, we're going to have less number of pixels. That means a smaller data set. If we have smaller pixels, smaller cells, it's probably we're going to need more of those pixels to cover the same study area, the same extent of the study area. But that also means we're going to have larger files, right? So we have a large file with very small pixels, it's probably going to be useful, but we also could have problems with computations, because we're going to have more computations happening because we have more cells, right? So there's this trade-offs between also computing time and also the size of the cell. So there are some advantages, but also disadvantages of the raster model. Yeah, in terms of how we're dealing with the attributes. So remember when I was talking at the beginning that spatial data is usually associated with non-spatial data. That means that we need to find ways of storing non-spatial data also with raster information, right? Now, in the raster model, we usually group pixels in regions, and we use the same value, the same number to represent those regions of pixels. So for example, in this representation here, we have some areas, right? We have 5 different types of land uses and land covers. As you can see, each region encompasses a series of pixels. So we usually group these regions again in groups of pixels, and all those pixels are going to have the same label, right? The same value in a discrete representation, a discrete map, for example, right? For example, a map of vegetation, a map of soils. And that's usually how we deal with the non-spatial component of the data. So maintaining a one-to-one relationship in raster data is not convenient because our attribute tables will be so big. You can imagine, for example, a small raster data set with, I don't know, maybe 1 million pixels, right? 1,000 by 1,000 pixels. 1 million pixels associated with 1 million rows in an attribute table, that will make a very large file, right? A very large data set. So we usually don't use that type of connection, right? So what we use with the raster data model is a many-to-one relationship. So many pixels associated with 1 row in the attribute table. Right, and 1 row in this table where we store non-spatial attributes. So many-to-one. So the many-to-one relationship in the raster world is an important one because that helps us save space, right? Save space and also reduce redundancy. We don't want to have many rows with exact same information, right? So instead of doing that, we group these areas in groups of pixels, and we associate 1 row in the attribute table with that group of pixels, right? And that helps us reduce the size of the files, and also it will help us with computations later on. So this is an example here on the bottom right. The raster many-to-one relationship is a very important one and important to keep in mind. That's how we organize data in the raster model. So this, usually in GIS, what you see is these conversations about, what are the advantages of raster versus vector. And as I said before, for example, raster data is relatively simple to implement, to store. The geometry of the pixel is constant, so it doesn't change. So in terms of modeling, for example, when you involve some mathematics in the manipulation of data, it's much easier to deal with raster data than with vector data. Vector geometries could be complex, and that also makes more difficult to work with complex geometries, right? So in terms of modeling, mathematical analysis, statistical analysis, usually raster data is preferred, especially when you're trying to develop some kind of a spatial explicit model, right? A spatial explicit geographic model. But again, if you are interested in, for example, creating a nice map, if the purpose of your project is cartography, right? Cartographic representation where detail is more relevant than the analysis, maybe that vector world or a vector model is more important, is more relevant because you can achieve the levels of precision that you need for your cartographic objective. So again, so there are advantages and disadvantages of each type of conceptualization, but this is how we do GIS analysis in general, right? Kind of dividing the world in these two different types of frameworks, right? The raster framework and the vector framework. Of course, there are different types of data that can be represented with both, right, in both ways. So, and an example of this is, for example, elevation, right? Elevation maps. Here, the top left, a map is a raster representation of elevation. This is a digital elevation model, or DEM. So each pixel represents elevation. So each pixel has an elevation value. Is a continuous variable, so we're providing a wall-to-wall coverage of elevation. Each pixel has an elevation value. But we also could represent elevation using vector contours. We can also use polylines, for example, to represent elevation. So this is another way of representing elevation. Each line is an isoline, so the value along the line is the same, and that represents elevation, right? So two different ways of representing elevation using a raster data model and a vector data model. But there are all different types of model. For example, there's this other one that's called the triangular irregular network, that is a three-dimensional vector model that is really good for example, data, to represent data in 3 dimensions, in 3D. So again, multiple representations of the same feature, right, of the same geographic phenomenon. So sometimes you just have to think about what is the purpose of my project, right? What is the purpose of my GIS project? Is this cartography? Is it communication with audiences? Is it more analysis, mathematical analysis? So depending on the answers to those questions, you're going to choose one or the other. And sometimes the more complex models or the most sophisticated models use both. But that usually requires a conversion from raster to vector, or from vector to raster. And you do that conversions, constantly throughout the modeling process. And that's a very common type of approach as well in more sophisticated modeling exercises. So we're not limited to just one world, right? But we also need to understand that the tools that were developed to work with vector data are different than the tools that were designed to work with raster data. So, and these are two different worlds. There are two different types of frameworks that you need to be aware that exist, and that some concepts that apply to the vector world do not apply to the raster world, right? So you need to also understand that there are differences in the structures, differences in the tools, and also in the language that we usually use to refer to these data models. So each data model is associated with particular formats. And in GIS nowadays, there are hundreds of data formats that we can use to represent geographic information. If you are familiar with GIS and you have used GIS in the past, for example, there's this particular vector format that's called a shapefile, right? The shapefile is a vector representation that uses points, lines, and polygon geometries to represent spatial data. And it's kind of a standard nowadays. So most GIS packages are going to be able to read and generate shapefiles. In the raster world, for example, there's, again, different types. One that comes to mind is the TIFF, right? The TIFF, TIF, GeoTIFFs. That's a common type, a very generic type of raster format that most or all GIS packages will be able to handle and also create, right? Create this type of model. So again, these are just some examples of data formats, and if they are raster and vector, right? Raster over vector. We're going to be working in the exercise that I prepared for today. We're going to be working with TIFFs. Again, we're going to use a raster approach in our analysis. So we're going to be focusing mostly on TIFF formats. But as you can see, there's, again, hundreds of data formats that we can that we can use in GIS. And the most complete GIS packages, the most sophisticated ones, should be able to read several formats, right? Dozens of formats. And the more formats, the better, right? Because again, geographic information can be stored in very different ways. Okay, so that leads us to this second part of the discussion about spatial modeling. And why are we building spatial models, and why do we do this, right? And I just put here that this quote, that when you study a phenomenon in the context of a particular location, you begin to better understand why it happens, where and when it does, and what conditions exist that could influence that phenomenon. So I think that's important in terms of providing a justification for spatial modeling. So we're not modeling just for the sake of modeling, right? We are modeling something to better understand that phenomenon. And when we create a model, we're kind of simplifying the problem, simplifying the phenomenon into its most important parts so that we can better understand the phenomenon. Right, so I've seen papers, and sometimes also students, for example, that who want to create a model just because it's nice, right, to have a map. But what is the purpose of that map, right? Why do you want to create a map of that particular feature, of that particular phenomenon, besides the aesthetics part of it, right? And this is when you have to ask yourself, right? What is the purpose of your model? What is the purpose of this particular exercise? So we start with a real world problem, right? And that's the objective is to better understand this problem, to find a solution to that problem. To find the solution to that problem, we need to kind of deconstruct this problem into different components. So in GIS, we're going to start with defining the different, we have to conceptualize that real world problem. So we can describe it, for example, we can use maps to describe the spatial problem, to represent the spatial problem, to show where the hotspots are, where the problems are. We can explain it, we can make predictions, right? That's how we're conceptualizing our spatial problem. Then we're going to have to find the data. Right? We need to find the data to represent the different features that we want to better understand. And sometimes to understand a particular phenomena, we need to find the other pieces that help explain or help predict that spatial phenomenon. So we need to find the data, we need to find the types of data for analysis and representation. And then once you do the analysis, I think the ultimate goal of your model is to provide information, right? So you have an audience, you have stakeholders that are contributing to a better understanding of the phenomenon. You want to provide some kind of description to that group of stakeholders, to that audience. So you want to use your map or your maps as communication tools, right? You want to use them as communication documents to convey information, right? To show what the problem is about. So that's what spatial modeling is about, right? And these are all the different pieces that you usually go through when you develop a spatial model. And the spatial models can be of different types, right? And we're going to talk about a few of them. So usually you could think about spatial models that are based on purpose, the purpose of the spatial model. Some of them could be based on methodology. And then some of these models can also be based on logic. So I'm just going to go very briefly through these different categories to better understand how we are kind of framing this, right? This concept of spatial modeling, right? And the different types of views and different types of approaches that we have to create the spatial models. So models based on purpose, again, we start with a spatial problem. And again, the spatial problem could be of any type, right? It could be of any type. It could be, for example, that we want to measure the geometric characteristic of the landscape. So let's say that you have a map of land use and land cover, a vegetation map, and you want to describe, for example, how big the forest vegetation is in comparison to shrubs, in comparison to exposed rocks. So that's a very geometric type of problem, right? And you're basically trying to describe the landscape, right? Describe vegetation. On the other hand, you have problems that are trying to find, for example, the best solution or the best area for a particular use, right? So we have, again, descriptive problems on one side and descriptive spatial models that are going to help us model the geometric characteristics of the landscape. And on the other hand, we have prescriptive models that are going to help us achieve a best solution based on some functional relationships between different factors, right? So again, so in terms of purpose, we have descriptive models, a vegetation map, a soil map, a land use map, right? That's a descriptive model. On the other hand, we have this prescriptive model that we combine a series of factors, we combine a series of criteria to find something, right? To find a place that satisfies all these criteria. That is a prescriptive model. So think about it as a prescription, right? If you want to do this, if you want to get healthy, you're going to take this medicine, right? That's the prescription when you go to the doctor. Here is the same thing, right? So if you want to find, for example, an area that is suitable for conservation, you're going to find areas that are far away from roads, that are public lands, that are forested areas, that have water, etc. So you have a prescription, and based on that prescription, you find your best solution, right? That's the modeling approach that we're going to follow today in our exercise. Okay, so I'm just going to jump. I want to start with the hands-on exercise earlier. So there are some other models that are based on methodology, right? These are deterministic. In other words, we know that relationships between the different factors. So in other words, if I combine X, Y, and Z, I get this product, right? I get this answer. If I combine A, B, and C, I get this other answer. So I know what the variables are, what the most critical variables are. I know how to combine them, and I get an answer, right? That's what we call a deterministic approach or a deterministic model, right? For example, if you want to find, for example, an area where you want to build a library or where you want to place a new fire station, and you know, and you have information, for example, about the people who live there, where the roads are, the parcels, elevation, land use, you put all these variables together and say, okay, based on this information, I have a solution for this, right? I know how these variables relate to each other, and this is my answer. There's a deterministic model. I know where I want to get. On the other hand, we have this other type of models that are stochastic or based on probabilities, that instead of knowing exactly where things are, we know a probability. We generate a probability of finding that particular object, that particular feature, and there's an associated error, right? And there's an error associated with that probability. So the probability of finding this particular species in this area is 80%, but there's a 20% chance that I'm wrong, right? So these are what we call probabilistic models or stochastic models that are based on probabilities. And we can generate maps that look something like this, right? Where, for example, here the peaks in red show areas of high probability. The valleys or these areas, the bottoms are areas of low probability. So we can generate a probability map showing the presence, absence of something, right? And this is a stochastic model using statistics, right? We can generate this type of spatial model using statistical analysis as well. So we usually combine statistics and spatial analysis to generate this type of stochastic spatial models. In our exercise, we're gonna go to the simpler, right? To the simpler approach. We're gonna use a deterministic approach, which is also very valuable and also good for our practice today. Okay, so I'm gonna, again, jump some of this. So finally, some of these models can also be divided or categorized by logic, right? So we have inductive models that rely on individual observations to generate or to come up with a generalization about that phenomenon. And then based on that generalization, we can come up with a theory, with a paradigm about that particular phenomenon. That's usually the approach that we follow in statistics, right? In statistics, we come up with a sample, we define a sample, we use some statistical analysis to generalize about our population. And then based on that generalization, we can generate a theory, right? That's what we call an inductive approach. And spatial models can also follow this type of approach. For example, there's particular modeling approach in GIS and geostatistics, for example, that follow that type of conceptualization, inductive conceptualization, where we go from individual observations to theories. On the other hand, we have deductive approaches where we depart from a theory, depart from a paradigm. For example, if we know, what are the factors that contribute to soil erosion, and we know, and we have a theory about soil erosion, we can depart from that theory and we can make predictions based on that theory, on that theoretical framework that already exists. And then we can say something specific about individual cases, right? So we're kind of going in the opposite direction as in comparison to the inductive approach, right? So we depart from the theory to say something about the individual cases, right? That's the deductive model. So in GIS, we also have those type of modeling, spatial models that follow the deductive logic. Okay. So again, for a complete discussion about these points, you can download the PowerPoint presentation that is available in the Google Drive. I'm just going to skip some of these other details because of the time, but I think it's important to keep those general concepts in mind, because we're going to apply them, right, in the exercise we're going to be working on in the second part of the session. So lastly, right, to have the concepts, the necessary concepts in mind, we need to also think about that there are different types of tools and different types of procedures that are used to work with GIS data, to work with vector data, raster data, and also to implement the different types of models that we talked about, right? Prescriptive models, descriptive models, deterministic, etc. Right? So there are different types of approaches. And in the raster world, right, in raster data, we usually rely on this particular type of conceptualization, or this particular type of framework that is called cartographic modeling, right? Cartographic modeling, again, is the modeling of spatial phenomena using maps, and usually using raster maps, right? So we can create a cartographic model to, for example, find an area that is suitable for conservation, right? So we can build our cartographic model using maps, using raster maps that are going to require some inputs, the definition of inputs, to come up with an outcome. And these inputs and outputs and outcomes are maps. And in that case of map algebra, these are raster maps, right? So map algebra is a language, is a framework that allows us to manipulate raster information using mathematical operators, right? Mathematical functions, mathematical operators. And we can combine these different types of mathematical functions and operators to create a cartographic model, right? So map algebra is the engine that is going to help us manipulate the data in a way that we can create other maps, other outcomes based on a series of inputs. And these inputs are going to be raster maps. So there are different types of examples of this, and a lot of examples in conservation specifically. And all this work started in the early 1980s, 1990s. And this language that is called map algebra was originally presented by Berry and Tomlin in 1994, where they actually compiled a series of operators and rasters to come up with, again, the theory that we need to implement this type of raster models, right? So Dana Tomlin and Joe Berry are kind of the mentors or the minds behind map algebra. So map algebra, again, can be envisioned as the rules and operational procedures that are employed with raster data, with the raster conceptualization, with raster maps to operate with maps. So the nice thing about map algebra is that we can apply all these different types of mathematical operations with maps, right? We can add maps, for example, map A plus map B equal map C, right? So we can create a function, right? Map A plus B equals C. And we can implement it, and we can generate more data based on that combination of maps, of raster maps. So again, map algebra allow us to do this type of operation with maps, right? With raster maps. So again, it's the basis of cartographic modeling. And we can generate solutions, GIS solutions, using this type of mathematical modeling approach, using maps, right? Using maps. So again, map algebra, operators and functions that allow us to combine, integrate raster maps, right? And that integration combination of maps using mathematical operators and equations is what we call raster overlays, right? Raster overlays. So we do all this type of kind of integration of maps using mathematics. So the mathematics of maps, that's what map algebra is about, right? So for example, this is an example of, if you guys are a little bit familiar with matrix algebra, right? Again, matrix algebra is a part of mathematics, and that allow us to work with linear functions that allow us to arrange numbers in matrices to combine numbers, right? To combine numbers, to operate with numbers and equations in a relatively simple way. So for example, these are two matrices, right? Matrices, matrix 1 and matrix 2. And if you want to add these two matrices, right, in matrix algebra, all you have to do is just look at where the numbers are located, and you just add them together. Or for example, if you look at the top left numbers, 5 and 3, and we want to use matrix algebra to sum them, right? The result will be 5 plus 3 equal 8. Then you move to the next cell, right? 4 plus 3 equals 6. Then the next one, 1 plus 1 equal 2. So the result is this, right? This new matrix that has, again, the combination of these two previous matrices with a result of the sum, right? That's how you will do this using matrix algebra. But let's now translate this into a map. Now let's think that instead of having these matrices of numbers, we have two matrices of cells. And again, these cells can represent different types of geographic properties. For example, let's say that they represent elevation, right? Or that they represent temperature, right? Temperature of 5, 4, 1 in, I don't know, Celsius, right? So we have two maps of temperature, and we want to, for example, come up with the average temperature for these particular locations. Remember, each cell is associated with a value, but is also associated with a coordinate. So we can add these two numbers of these two cells, and then we can divide that by the number of cells to combine to obtain, for example, the average temperature at that particular location, right? So for example, here I'm just going to do the sum, right? So we have map A and map B. And the way that we operate here is exactly the same as we do it in matrix algebra, right? So we look at the cells and the corresponding cell at that particular location, and we add the values, right? 5 plus 3 equal 2. So the new value of this cell is going to be 8. the new value for the second cell, 4 plus 2 equals 6. The next value is going to be 6, right? So we have this new raster data set, this new raster map that has the sum of both of the previous two maps. This map is now a combination, a linear combination of these two previous maps, right? Now, this is the simplest example. Now, if you can think of any other types of mathematical models, ecological models that could be represented spatially, you can start seeing the value of this type of mathematical approach to develop complex geospatial models, right? Again, the result of the model is an outcome, is a map, is a raster map that shows the combination of the other maps, of the other raster maps, right? So if we want to multiply, for example, these two maps, we have map 1 and map B for some reason, right? This is just an example, a hypothetical example. We want to multiply. Again, we do the same thing, right? So for example, 2 times 3 equals 6, and the value of the new cell is going to be 6. 4 times 2 equals 8. So this is done on a cell-by-cell basis from left to right, from the top to the bottom. So that's the order of the spatial order, how the operations are performed, right? Left to right and top to bottom. And then you look at the corresponding cells, and then you do the operations on a cell-by-cell basis. So all these type of operations on a cell-by-cell basis are called local statistics or cell-based statistics. And that is a particular type of functions, right? There are a series of functions that fall within this group of local statistics, local cell-based statistics. There are more, right? There are different types of functions that could be applied, but this is what we're going to be using in this exercise, a local cell-based statistical approach in map algebra, right? Using map algebra. So again, as you can see, we can combine maps mathematically, right? This is a map overlay. And these are just some of the common raster operations that we can do with maps, right? The plus, minus, again, relational operations, bitwise operations, etc. So there are a series of operators, mathematical and logical operations that we can apply. But think that the key thing here is that we are operating with maps, right? The variables that we use are maps, right? Raster maps. So in the concept, in the exercise, we're going to be using one particular type of approach that is called multi-criteria evaluation. In multi-criteria evaluation, we usually follow these steps, right? We start with the definition of what my spatial target is. For example, in the exercise that we're going to be working on, we're going to define an area for conservation, right? We're going to say, okay, we're interested in defining this area, this particular area for conservation. So that's our spatial target, right? The areas that you want to identify. It could be anything else. It could be, for example, an area for the construction of a new library, an area for, I don't know, the placement of a new supermarket, right? So whatever your spatial target is, that's the definition that you have to start with. Right? What is the spatial target in your problem? So define a spatial target. Then you need to define what are the criteria that are going to help you select that target, right? Identify that target. Right? For example, we're going to be using some criteria in our exercise. For example, we want our conservation area to be farther away from roads, right? So distance to roads is a criteria. We want it to be in areas where high elevations, in the upper part of the watersheds. We want to be areas of forest. So those are the criteria that we want to meet, right? Again, and the exercise is just a hypothetical exercise. These are criteria that you will have to define with a series of stakeholders, with a group of experts that are going to help you define what are the criteria needed to define your targets, to identify your targets, your spatial targets. So once you define the criteria, then you need to operationalize the criteria. That means you need to find the data, right? You need to find the data, the GIS data, the remote sensing data, the climate data, biological data, etc. But the key thing here is that the data has to be spatially explicit. That means that information has to have a coordinate, right? A coordinate associated with the data. If it's non-spatial, well, unfortunately, this modeling framework would not work, right? So it has to be a map, and that map, could be a raster or vector map, but at the end is going to be transformed into a raster map that we can use map algebra to operate with. So operationalization of the criteria and spatial variables, that's the next step. Then, think about this. You have a map of temperature, then you have a map of precipitation, you have a map of distance to streams, a map of elevation. So there are all these different units that are incompatible, right? So how do you make those variables compatible? You have to transform them in a way that you can use, that they are going to be set to the same scale so that you can combine them and integrate them, right? So you need to transform those variables using a common scale so that you can combine them. So the next step after you have your variables is to transform them, to transform the scale. Then you have to think about that maybe some factors are more important than others. So let's say in our example of conservation, maybe distance to roads is an important one. So you want the area to be very far away from roads. So your distance to road variable is probably going to be the most important one, so that you're going to give that higher weight. The weight means more important, right? More important for the model. So you define the weights. Again, the weights are usually done either using, based on literature, based on conversations with experts, based on participatory approaches where you bring different stakeholders to have a discussion about the problem. So it could be, this moment of weight assignation, it also helps to bring back the people who are interested in this project, who are the stakeholders, right, who are interested in this, to bring them in the conversation to help you define the results, right? Find the areas for conservation, for example. So it's not done solely by the analyst, right? So here's a moment of input from external agents. And then you will be able to localize, identify, select the areas that you're interested in based on some kind of prioritization to identify these spatial targets. Okay, so just an example, right? So you have the different variables. Again, the different variables are going to be raster maps. Let's say you have aspect, slope, distance to roads, temperature, precipitation. These are all geospatial data sets. So identification of areas suitable for conservation, that's your target, right? That's your goal, the goal of your project. That's going to be dependent on all these different factors, right? The suitable areas are a function of all these factors. Each factor is going to be associated with a weight, the weight basically representing how important that factor is in identifying the areas for conservation. If you do this, if you assign these weights as percentages, which is probably the most common approach, right? The sum of the weights has to be equal to 1, right? So then now that you have the concept, the conceptual model in place, you need to find the data that are going to help to implement the model, right? And how do you do this? Then there are different types of data repositories of remote sensing and GIS data, climate data, etc., that you can rely on to derive the information that you need. Remember, the specialization of factors is key. So that means that we need to find maps, right? Maps of these factors, maps showing the spatial variation of these factors. So after that, the next important step is to transform the variables, right, to a common scale. For example, we can transform them, all these maps in the scales from 1 to 10, 1 being not suitable, 10 being very suitable, right? So a common scale that we can use so that we can integrate them. So the result, right? The outcome of the integration of this map is going to be a very similar map showing areas of low priority to high priority, right? So that's the goal here, is to come up with a model, with a suitability model that tells you areas of high suitability and low suitability. We want to avoid binary representations, for example, suitable, non-suitable, right? Because that's not very powerful, and you cannot generate too much discussion using those type of binary representations. So we want to generate a map that allows for discussion, right? Areas of high, medium, low probabilities or low suitabilities, right? Those are probably more robust outcomes in any type of a spatial model, instead of zeros and ones, right? Suitable, non-suitable. And at the end, you get something like this, right? A map showing the conservation priorities, high priorities, low priorities, based on all the series of criteria that you analyzed, right? That's what we call multi-criteria evaluation in the context of suitability analysis. Okay. All right. So I think that's all what I wanted to talk about today in terms of basic concepts. What I would like to do, so let me see. So right now it's 2:05. So there are 56 participants in our session today. And I'm sure there are some of you who don't have the software, and that's fine, But what I would like to do is work on this other exercise that I prepared. And so let me just share my screen one more time very quickly. So if you go to the Google Drive link that Anna provided at the beginning of this session, there is this PDF that has, again, some guidelines and instructions about what to do. Since this is a workshop, I think it will be more useful for you guys to play with the data, to play with the software a little bit. And I don't think we're going to have the time to complete it, right? Because we only have 50 more minutes. But the instructions are here, right? The instructions are here. I think it's very detailed. So if we don't have the time to complete this exercise here, I think you can do it on your own. But there are a few things that I wanted to talk about before we jump into the exercise. So first of all is well, this is a hypothetical example, a hypothetical problem. The idea is that you are working for a conservation organization. This is in Washington State. The data that I collected is from Washington State. And you have been tasked to identify potential areas for conservation. So that's the goal, right? So you already have a goal in your problem, a definition of the problem, right? So this is a project in collaboration between private and public organizations, sponsored by Washington State. So you collect a series of GIS layers to better understand the landscape. Remember, that's the first step in the process, right? We need to understand what we're dealing with, right? So you collect the data, some data that is going to help you analyze, better understand the region, and identify areas for conservation. So you meet with a group of stakeholders and you decide what are the conditions, what are the criteria that should be met for these areas to be prioritized. So these are the criteria, right? So, for example, potential areas for conservation should be in public forested lands, because this is a project sponsored by Washington State. The areas should include high elevation water bodies, glaciers, wetlands, forests. So those are particular land cover types, ecosystems that we want to conserve, that we want to preserve. Right, so that gives you a sense of what a priority is, right? What our priority area should be. The other criterion is that this area should not be used for agriculture or could be used for agriculture in the future. So that means that areas with gentle terrain and close to streams should be excluded because those are usually areas used for agriculture. So we want to be areas with we want to preserve areas with irregular topography, steep slopes, far away from streams. The area should also encompass the upper portions of the watersheds. That means areas of high elevation. And the area should be located away from roads and highways. So those are the 5 criteria that we're going to try to meet. Again, as this is a hypothetical example, this is the definition of the problem that the organization has given to you, right? This is usually done in a more participatory framework, right? When you have all these discussions about what are the important criteria, but since this is just an exercise, we're going to be relying on these 5 criteria. Again, we're going to be using a multi-criteria evaluation approach. And we're going to be using QGIS to do this. In terms of QGIS, especially for those of you who have never used GIS or who have little experience with GIS, this is how QGIS looks like, right? This is the interface. And many GIS software look very similar, right? But I think the most important pieces here that you have to kind of think about are 2, right? One is what we call the table of contents here in the lower part. This is the table of contents pane. And then we have the map viewer, right? Or the map view pane where we can actually see the data. So when you bring data into QGIS, you need to think about that, you will organize your data here in the table of contents, and you can see the data here in the map viewer. Now, something interesting about this GIS package is that the order in the table of contents affects the way that you visualize the data in the map viewer. So, for example, if you have your streams layer first, that's the first map that you're seeing, right? That's on top of everything else. So, for example, I'm going to turn that on. I'm going to put elevation. So, as you can see, streams, right? The stream layer is on top of the elevation layer, right? I can turn this on and off, right? Just to visualize and see or not see the actual layer. But I can also move, right? You can drag and drop, for example. I can drag and drop the elevation layer and put it on the top. And now that's the first layer that I see. So if I turn on, for example, the stream layer, I cannot see it. Right? I cannot see it because it's under the elevation layer, right? So that's important for you guys to think about because sometimes, people get confused and say, why the stream layer is not there? I cannot see the stream layer, for example. Oh, it's because the elevation layer is covering the stream layer. So the order in the table of contents, it's important, right? So if you want to use, for example, if you want to visualize lines or points on top of polygons, you will have to have the points, lines on top of the polygon, right? So here, for example, the stream layer is just a series of connected pixels, right? And if you want to see it on top, right, you need to make sure that that layer that is covering the whole study area with information is the last one in the table of contents, so you can see it. So again, you can turn on and turn off the layers here. All right, so a couple of things that I think important for you guys to keep in mind is, again, when you want to add information into QGIS, again, you have a main ribbon, and the main ribbon is basically the principal ribbon where you have all the drop-down menus necessary to work with data and to do analysis or create maps. So this is the main ribbon of QGIS. And one of these drop-down menus is called layer. And under layer, you have different types of operations you can do with layers, with the different spatial layers. And one of them, a simpler one, is just add layer. And as you can see here, you have 2 options, right? Add vector layer if you're working with vector data, or add raster layers if you're working with raster data. So just make sure that you understand this differentiation, right? Now, we talked about the difference between vector and raster, and that's why you have it here as well, right? So in this example, we're going to work with raster data. So when you add data, make sure that you select this option, add raster data. Okay, so the rest, right? We have all these instructions here. So what I would like to do now, and maybe Bernie can help me, what I was thinking about is dividing the group in a small group. So we have 55, 56 participants. So I was thinking maybe groups of 5 people each, so about 10 or so, 11 breakout rooms. Maybe, Bernie, you can just separate them and assign people randomly to the different groups. Hopefully, you all will have the program that we need, QGIS, and try to follow the guidelines, the instructions here. And I think it's better when you guys learn from each other. Instead of me telling you, do this, click here, I think it's important for you guys to do it yourselves. Use this as the PDF as a guideline. But if you have problems, try to troubleshoot them with your peers, right, in your small group. And I think that will help you learn. Maybe not in the most efficient way, but I think it will be, you will remember the most, right, if we follow this approach. So Bernie, why don't you help me with creating the breakout rooms if possible?
Yep, breakout rooms are ready to go, so I'm going to open them for everyone. If you need to leave the room for whatever reason, or you have a question, just put it in the chat and I'll communicate it to our 2 co-hosts. Here we go.
So I'm putting here in the chat also the link to the PDF to the exercise in case you were not able to access the Google Drive. This is the direct link to the PDF with the exercise.
Let me send that in a broadcast message.
Okay. And also, Bernie, if you could broadcast if people have questions, specific questions in their breakout